Hello, I'm here to talk about my favorite Desmos feature, which is the regression feature. The regression allows you to solve very easily and simply for numerical approximations of equations that would be difficult to do even with a sophisticated computer algebra system, and this lends for very nice and useful calculator functions. So let's say I have a variable a, and let's start a off at 10. Um, and then let's make up a function here. Say f of x is x squared, and we have a graph of it over here. And let's say that we're going to try to find a value t so that the integral of x squared from 0 to t is about a, whatever that is. So we could simply do this by saying the integral from 0 to t of f of x with respect to x is about a. And right there, it gives us the value of t for which approximately that would be true. And then you could do some things like, well, let's graph the error between 0 and f of x subject to 0 being less than or equal to x less than or equal to t. Sorry, y between that. And then over here, we could see that area. This area here is 10. And we can certainly see then that as we decreased or increased the value of a, that the parameter t would change, and that that graph underneath, or the area underneath this graph would also change as a result. Great. So this is useful, of course, in calculus or courses like this to try to, explain the concept of errors in the curves when you're doing demonstrations in the class. But what I find really, really useful about this is when I created a calculator for Z hypothesis testing. So this is the calculator for Z hypothesis testing. It's also the calculator that I'm submitting with my application. And what we have on the side here, and let's scroll up a bit, is on the side here, in the first part, we have all the information that we need for hypothesis testing about our sample, the size of the sample, the mean, and the standard deviation. And so let's make some stuff up. Let's say our sample size is 30. Let's say the mean of our sample was 100 for now. Let's say the standard deviation of our population is 20, say. And then we can have down here, there's a tab here for computing the confidence interval. We have our alpha here for acceptable level of significance. Let's set it to 0.05 maybe. Um, then what these different tabs here will allow you to do is to look at and uh, test different hypotheses for different possible values for the true mean. And the way that this is done is we have the normal curve uh, formula here, and then I use the regression function to create a z from the left, a z from the right, and a z from the center for the left, right, and uh, center z-scores for the left tail, right tail, and true tail tests that are related to the hypothesis testing. So let's go back up here. Let's say we want to claim that our sample mean is 100, and let's say that our proposed true mean is 100, and let's say our sample mean is 110. Uh, could I make this claim that the actual true mean, say, is 100, or is it that or do I have to accept the alternative hypothesis where the true mean is more than 100? Well, let's take a click here. With an alpha of 0.05, we see that any observed mean of 106 or greater is going to force us to reject a null hypothesis and accept the alternative hypothesis. And this is equivalent to a z-score of being greater than 1.6044. And of course, with a sample mean of 110, that gives us a p-value of 0.003. Now, this green area here and this value here, that's tied to this z-score here, which is itself tied to the right tail region. If we go down to our visualization, we see that alpha is meant to be about z from the right up to 10, and 10 standard deviations away, it may as well be infinity. And this area under the normal curve here is meant to be about 0.05. Now let's say if I were to drop that down to 0.005, that shifts things forward quite a bit. And if I were to say 0.005, then that definitely shifts things over to the right by a huge amount, or not that huge I suppose, but up to 112. And all that's going on here is in this tabulation here, that 0.005, 05 is the area between 3.3 to 10 under the standard normal curve. And then what the calculator does is take that z-score, translate it into actual x value of 112, and then draws the appropriate region. If we make our alpha value or level of significance to be something a little bit less ridiculous, like again, let's say 0.01 maybe, 0.001, then we see over here, if we make it up to 0.01, then now that z value is 2.326 something, and now we can accept the alternative hypothesis. But the point being that all of these various tests are done with the same way. I can't use the same variable, obviously, but I have a z from the left, which computes an area between -10 and z from the left to be about whatever we've set alpha to be. And then there's the central alpha, which says that the area from 10 to zc is half of alpha. So it's pretty good about letting both sides of the equation here be algebraic expressions. And in all of these cases, it yields the appropriate z-scores. And so all of this allows me to create a very robust and practical hypothesis testing calculator that not only yields rejection regions and p-values, but also visualizes the rejection regions and the interaction between the proposed true mean and the sample means, which, so it's not just useful from a practical point of view, it's also useful as a pedagogical tool to give students an intuitive understanding of what's happening when one attempts a hypothesis test, what's been measured, and how they should think about or visualize these things. And none of that would be possible without solving these integral equations here. Now as we, these integral equations here, now as we know, e to the minus x squared over 2 does not yield a nice antiderivative, so solving it directly that way would be cumbersome and difficult to say the least. But by using the regression, it's as a matter of just setting up this sort of equality here. All right, thank you, and thanks for listening.